Hi, I want to talk about the property of inductive reactance that we see in AC circuits. Now, the key with inductive reactance is the word AC, because it's not something that can happen if we hook an inductor up to a DC power supply. Because an ideal inductor has absolutely no resistance. So an ideal inductor would really just be a wire, and if you hook a wire up to a power source, you would get virtually infinite current. So the idea of inductive reactance is as a current changes through an inductor, there's a self-inductance that's responding inside that inductor, which is limiting the ability for that potential difference to have a current move through that inductor. So if we were to apply Kirchhoff's law to a simple AC circuit where we have an AC power source and a single inductor, Kirchhoff's rule says the potential difference from our power supply minus the inductance in our inductor times the derivative of our current with respect to time is going to equal 0. So that means then that our potential difference, our maximum voltage times the sine of omega t plus any phase angle phi, is going to equal the inductance times the derivative of current. So let's calculate then the current that we would get. So we need to solve this for current, which means I'm going to move everything that isn't my element of current di to the other side. So I multiply both sides by dt, I divide both sides by the inductance L, so that means that a small amount of current di would be equal to my maximum voltage divided by my inductance times the sine of omega t times a tiny element of time dt. So to get the current, I just need to integrate that little bit of inductance, or little bit of current di. So I would end up with Vmax over L, constants pulled outside, and the integral of the sine of omega t plus my phase angle with respect to t. Now the integral of sine is going to give me minus the cosine. And through u substitution, I need a factor of 1 over omega, so that means my integral is going to be minus Vmax divided by omega times my inductance times the cosine of omega t plus that phase angle. So this looks really similar to the current function that we saw with resistance. With resistance, we said the current, if I just have a resistor, is Vmax divided by my resistance, and then I would have the sine of my oscillating term. Here, I have the cosine instead of the sine. So that means that my voltage and my current aren't doing the same thing at the same time. In fact, my current happens to be 90 degrees or pi over 2 radians behind my voltage when I take a look at the two graphs simultaneously. Now, if I were to multiply those two functions together to look at the power delivered, I would end up with sine times cosine, which ends up through trig substitutions giving me the sine of 2 times my phase divided by 2. Well, the average of the sine is 0. So the average power delivered here is 0. So resistance is delivering real power through heating to that resistor. With this reactance, there's a current because the circuit element is responding to the potential difference, but we aren't losing any energy. We aren't transmitting any energy into heat. We're just sort of putting it onto that inductor, taking it off of that inductor as the potential difference, and the current is continuously changing. But this piece in the denominator behaves very, very, very similarly to resistance. It has units of ohms, just like resistance, but because it's responding to what the voltage is doing, not dissipating energy, we call it reactance. Specifically, inductive reactance. And the symbol that our book uses for reactance is a capital X with a subscript L for inductive reactance. So the reactance of an inductor is equal to the angular frequency of our power supply, 2 pi times our frequency in hertz, times the inductance of our inductor. Thanks for watching.